Okay, last lecture, we started talking about our shapes. We finally got to look at what are the shapes that we're talking about when we're talking about our quantum numbers, because we've got our principal quantum number n, and that describes the shell that we're in. If we're thinking about the Bohr model, or if we're thinking about like a solar system, our n equals 1 is our innermost planet, n equals 2 is our second planet, n equals 3, that's us, right? Earth, that's the third planet, the third shell, the third ring. I should probably know all my planets, but I don't. So that's fun, I like the order. So that's our principal quantum number. And then underneath that, we've got L, and L describes the type of shape that we're in, or the subshell. So principal quantum number or shell, this is the angular momentum quantum number. And this describes the family of shape that we're dealing with, also called S, P, D, and F. This is the type of shape that we're in. So our s orbital is what we're looking at here, and that's when our angular momentum quantum number is equal to 0. And then we also have within that m sub L, our magnetic quantum number. And that describes which of the particular shapes we're talking about within that family of shapes. In the case of our s orbitals, we just have one, because m sub L is from the range negative L to positive L, and if L is 0, then the only value that we can have for our m sub L is 0, so we only have one orbital. And our 1s, click the wrong button, our 1s orbital is our lowest energy orbital. It's roughly spherical shape. It is spherical shape. And this is always where we're going to start if we're adding in electrons. It has no nodes in the 1s. If we go up in our n number, then we get those nodes, those places where we can't have electrons or they don't exist. Our probability is 0. If we go to L equals 1, our angular momentum quantum number equals 1, these are the p orbitals. So every principal energy state above n equals 1, so starting in n equals 2, we also have the p orbitals. So that's, again, L equals 1. And our m sub L values, our magnetic quantum number values, go from -1 to +1. And so we've got 3 orbitals. Orbital is just talking about the individual shapes that we have within that shape family. And so our 3 orbitals are px, py, and pz. These are 2-lobed orbitals, so they've got 2 ends, and they each have 1 node at the nucleus for a total of n nodes. And if we look at our p orbital shape, this is what they look like. So they kind of look like a dumbbell or a peanut. Like in the shell peanut, a normal shaped peanut. And these are our 3 different shapes that we get. So our px orbital is along, it's lengthwise along the x-axis. Our py orbital is along the y-axis. Our pz orbital is along the z-axis. And this is a common representation that you'll see. Other times the ends of the peanut are a little bit more squat and short, sort of looking more like the head of Toad from the Mario games, kind of mushroom cap shaped, a little bit more squat and not quite as pointy. It doesn't really matter. The general idea is that we've got these 2 lobes and then a node in the middle. So the electron's not going to be found in the middle. That's where a nucleus is. If the electron was at the nucleus, the world explodes. It's not there because the world hasn't exploded, and so we know that it's probably out here instead. Also math. So we've got a bunch of calculus and calculations and stuff that people have figured out. They're out there. So P for peanut, and we've got 3 shapes. And then our d orbitals, this is when L equals 2, our angular momentum quantum number equals 2. And this first appears in n equals 3, because our rule for L is that it goes from 0 to n minus 1. So if n equals 3, then we can have L equals 2. Otherwise, it's not allowed. Anything higher, we can also have it. And in our L equals 2, since our m sub L goes from negative L to positive L, we get negative 2, negative 1, 0, plus 1, plus 2, for a total of 5 orbitals. And if you thought that the jump from S, our sphere, to our P, our peanut-shaped orbitals, was scary, this is another step up in terms of their complexity. So we've got 5 d orbitals, and the naming is a little bit less friendly as well. It's not just S, it's not px, py, pz. We've now got 2 axes showing up in here. So 4 of our orbitals are aligned with different planes, so 2-dimensional spaces. So if you take like x, y, and you make that a whole like flat surface, they might exist in that plane. You could also have xz, you could have yz, xy would be this way. Anyway, so they're in those like flat, they're 2-dimension spaces instead of just being oriented along one axis. And our 5th orbital, the dz squared, is along the z-axis. These are mainly 4-lobed. One of them, this dz squared one, is 2-lobed with a toroid. Does anyone know what a toroid is? It's not the thing that's in energy drinks that makes you go crazy. That's taurine. It doesn't actually make you go crazy. A toroid is a math word for a donut. So that's all that a toroid is. If you go to higher n numbers, then they're also going to have spherical nodes. We're not going to worry about that. We're not going to look at that. So here's our d orbitals. I usually think of d orbitals as double dumbbell, because P for peanut, they're sort of dumbbell shaped. So D, they're double dumbbell shaped. And this is true for our 4 that are in the 2-dimensional flat surfaces. It doesn't really work as nicely with our dz squared orbital, but it's just weird. So the naming, not that you need to know the like specific orientation of these, but just in case you are curious, our dyz orbital, dxy, and dxz orbitals, these are in between the 2 axes that are named. So the dyz is in the yz plane, and the nodes are along the z and the y axis. So there's no electron density there, and these lobes are pointing out into the space in between those nodes. The nodes where there's no density, the lobes where there is density. And then the same thing for the dxy and the dxz. For the dx squared minus y squared, the lobes where we have electron density are pointing along the x and the y axis. So lobes between y and z axes for our x squared minus y squared on the x and y axes. And then our dz squared, our lobe is along the z axis. So we've got our 1 dumbbell on the z-axis, and then we've got our donut, our toroid around it, our ring. Do we have questions so far about our s, p, or d orbitals? I would say the big things are to know kind of vaguely what they look like. Like if I showed you a picture of a p orbital, you should be able to say that's a p orbital. I wouldn't expect you to tell me that's the px orbital or that's the pz orbital. Just that's a p orbital because it looks like a peanut. The dz squared is the only weird one in the d orbitals. Otherwise, they're all these double dumbbell shapes. So again, I might show you, here's a d orbital. You know, I wouldn't expect you to know which one it is. Just you should be able to identify that it's a d orbital. You should be able to tell me what the angular momentum quantum number is. We are not going to be labeling any of these with their m sub l, their magnetic quantum numbers, but they do those labels, the -2, -1, 0, +1, +2, those correspond to specific d orbitals. I don't know what they are. I don't expect you to know what they are either. But if you take P-Chem, then maybe you'll be expected to know that. Third year chemistry. Okay, and now we've got the scariest, but the last ones. The scariest, but the last ones. Again, no more after the f orbitals. The f orbitals is our highest number. We start to see these in n equals 4 because L equals 3. So n has to be 4 or higher since our L values go up to n minus 1. And these are other orbitals, right? So for S, we had 1. For P, we had 3. The next odd number for L equals 2. For our Ds, we had 5 orbitals. And now we're jumping up, we've got 7 orbitals. So they increase in odd number increments. And they go from -3 to +3. And these are mainly 8-lobed. Our D was mostly 4-lobed. So we've doubled the amount of lobes that we have, the number of pointy bits that we have. I don't have a fun memory tool for remembering F. We don't even look at them in Chem 20. They just look kind of scary. And if you didn't like dxy, dxz, dyz, those names, you're going to hate these ones. They're awful in comparison. These are also going to have nodes if you go up to numbers above n equals 4. So like with our s orbitals, we had the places where there weren't any electrons, like cutouts when we went to the higher n numbers. We also get that with p, d, and f orbitals. Okay, here's our f orbitals, and we're just going to look at them and appreciate how crazy they look. So our f, x, y, z orbital has 8 lobes, and it looks like all between the x, y, and z planes, like pointing out in different directions. And then we've got fun combinations of, it kind of looks like the x squared minus y squared in terms of the naming, but we've got another thing in front and we're switching it up. And then we've got 3 that have 2 donuts and then like a cutout in the middle. So they're just the craziest looking ones. And imagine if we added nodes, more nodes for higher n numbers. They'd look even crazier. So there's our f orbitals. They're big, they're scary, they're freakish. F for freak. So we get all of those orbitals from mathematical wave functions. We talked very briefly about wave functions, their probability distribution functions. It says where are the electrons likely to be based on some things that we know. And that's how we come up with these crazy shapes. And they look crazy because that's what the math tells us that they are supposed to look like. Wave functions can have positive or negative values, and it can also have nodes where the wave function is 0. Our 1s has no nodes, but we get nodes as we increase our L value. So 2p has 1 node, 3d has 2 nodes, for F has 3 nodes, for example. That's why they start to look really crazy, is because we've got 3, basically like if you took a big knife and you chopped it once for every node. That's why we get such crazy looking things when we get to our F orbitals. So ignoring the ones that have the donuts, because we've got like conical nodes, which is fun. But like for the F, X, Y, Z, you can see like we made a cut along the XY, we made a cut along the YZ, and then we made another cut along the XZ planes. So we just like swung a giant sword through it, and then this is what was left over after we were done cutting it up. So that's the 3 nodes. For our p orbitals, it looks more like we started out with a log and then took a string and like snapped it. Like we tightened down our string too much and it like cut in the middle. Right, so this is our 1 node. So that's the nodes that we're talking about in this slide for the phases. When orbitals interact, their wave functions may be in the same phase or the same sign, or they might be in opposite signs. And we're going to be looking at that a little bit in later chapters. We'll take a look at like the very most basic, what is a phase. Listening to emo music maybe is a phase. So our phases, our 1s orbital, it's just positive. We just have positive. If we go up to our 2p orbital, here's our node. And part of this is positive and the other part is negative. So this is what we're talking about on this previous slide. Their wave functions may be in phase or out of phase. So if we imagined putting another 2p orbital next to this, we could have it be the same, and that would be in phase. The positive sides are matched up, the negative sides are matched up. This means that they can sync, they can line up. If you think about like electrical plugs, some of them have a big side and a little side. That's sort of what we're thinking about here. So like electrical plugs will have a small side and a big side. And basically we need the plug to match the outlets, since some outlets have a big side and a little side. If they don't match up, you can't put it into the outlet. You would have to flip it to get the signs to match up so that you can stick it into the plug. It's a safety feature, but for these, it's math and physics more than it is safety. But again, that's like beyond this chapter. We'll talk about it again in a future chapter. That's chapter 8. Any questions? Cool.